if you really understand what the differential is, which is what I explained a couple weeks ago, right? I explained what the differential is. So if the function is differentiable, this df makes perfect sense as a certain linear function. And you can apply to these functions like df, dx, and dt the same rules that we apply to everything. And so in particular, we can actually cancel out dx in the numerator and denominator, and that's what this formula really is. This formula is very elementary. It's just a statement that you can cancel out this dx in these fractions. You see? So there's no mystery. I mean, the way maybe it was presented before, it was kind of mysterious. But in fact, there's no mystery. If you make sense out of differential, if you explain what it is, then and the function is differentiable, in other words, that the df actually can be defined, then you can actually apply this rule. And you can just cancel out this numerator and denominator. Understood the conditions, right? So that's a chain rule for one variable. So now let's suppose that you have a function in two variables, f of x, y. Okay? But x and y are in turn functions of another variable which we'll call h. So now I would like to calculate what is df dh. So let me draw it by following diagram. So this is f. F is a function of x and y. And x is a function of h, and y is a function of h. So then f becomes a function of h by composition. Right? Because for each value of h, you'll have some value of x and some value of y, and then you plug them into f and you get some value. So effectively, you get a function of h. Right? So it's like a chain of two functions, or more three functions. There's f, there's this function, and this function. And by substituting this functions g1 and g2 into f, you get a new function of h. Once you get a new function of h, you can ask what is the derivative of this function with respect to h. And of course, in all this discussion, I'm assuming that this derivative exists, which is of course not guaranteed. Certain conditions have to be satisfied for the function f, g1 and g2. But in all of our examples, those conditions will be satisfied. So I'm not sort of focusing on those conditions too much. I'm just trying to explain the formula which we'll get once these conditions are satisfied. And so what is this formula? We have to compute df dh. Right? How can we do this? Well, we have to remember the formula for df, which we had 2 weeks ago. The formula for df was f sub x dx, or actually let me write it by using this notation. It will be slightly better. Remember that we had two possible notation for partial derivatives, df dx or f sub x. So I'm just using this one, but it's the same as f sub x. dx plus df dy dy. So that's df. Let's substitute in this formula. We just need to divide this expression by dh. So we'll just divide it here and here. Right? So what we'll get is df dx dh, dx dh plus df dy dy dh. See, so we got a very simple formula for the derivative of f with respect to h. And it's very similar to the old formula. In the old formula, we have to differentiate by x and then x by t. But now there's sort of two channels. There are two channels with respect to which f could depend on h. The first channel is through x, the second channel is through y. So through x, it depends in this way. You have to take the partial derivative of x with respect to x, and then the derivative of x with respect to h. And through the second channel, you get the second term. But it's very easy to remember if you draw a diagram like this. Note that in this formula, I cannot cancel these guys out, because while dx actually makes perfect sense as a differential, this curly df or dx doesn't make sense by itself. Right? I think I explained this when we talked about partial derivatives. The notation is just for the ratio, and this is partial derivative, but this and this by itself doesn't make sense. So I can't prove this formula by canceling out things in numerators and denominators. Instead, I'm proving this formula by using the formula for the differential, and I'm just dividing this formula by dh. When I divide on the left-hand side, I get this expression. When I divide on the right-hand side, I replace dx by dx dh. I replace dy by dy dh. That's the formula I get. Okay? So that's the formula for the derivative when you have this chain of functions. Why am I explaining all this? Because I claim that I can calculate the formula for the directional derivative by using precisely this rule. For the following reason. I can think of this function as a function in which is obtained in this way. Namely, I will just say that I have a function f of xy, and then I will have x is equal to x0 plus h8, and y is equal to y0 plus hb. Right? So this is what I called in this general setup by g1 of h and g2 of h. This is g1 of h, and this is g2 of h. They're very simple. I just take them from the formula for the directional derivative. So now I can apply this rule. So the point is that du of f at x0 y0 is exactly df dh, in which then I substitute h is equal to 0. Right? Because what I'm doing is I'm just taking this function, the composition of these functions, when I make exactly this, that I have f in which I substitute x0 plus ah and y0 plus bh, and I take its derivative at 0. Taking the derivative at 0 precisely means that I subtract the value at h equals 0, and the value at h equals 0 is exactly x0 y0, which is what I have, and I divide by h and I take the limit. So this is just rewriting this ratio. This ratio can be considered as a derivative of this composition of functions at h equals 0. But now I can calculate this derivative by using the chain rule. Right? So I use the chain rule. So what do I get? I have to get, which is just this formula. So I just get df dx times dx dh. What is dx dh? A. That's right. This is a linear function in h, because x0 is fixed. Right? x0 is a constant, a is a constant, and h is a variable. I view this expression as a function of h. It's a linear function. We're used to this kind of things. When we talk about equations for lines, we will have x0 plus ta, for example. Right? So, but usually we call our variables x, y, z, or t. Now the fancy thing is that I'm using this letter h for the variable. But of course we realize that we could use any variable. The reason why I'm using h is because in some sense, it's an auxiliary variable, so I don't want to mix it with the other variables we've used, because in some sense it plays a very special role here. And also in the book, like h is used. So in other words, there are some reasons for using h which have nothing to do with the subject matter. Right? It's just a matter of convenience or custom and so on. And if you view this as a function of h, it's just a linear function in h, and as such, its derivative is just a, just a coefficient in front of h. So this is a. I'm sorry, this is a. This let me just write it here. dx, dh is a, and likewise dy, dh is b. So therefore, the second term is df, dy times b. So finally, we get the formula for the directional derivative. The directional derivative with respect to a general vector u, which is ab, is just, and I want to write it a slightly different way, a times, oh, it doesn't matter, I can write it in this order, fx of x0, y0 times a plus f sub y, x0, y0 times b. Just this formula, but now I switch back to the old notation, f sub x, f sub y. The reason why I use this notation for chain rule is because if you write it in this way, it's easier to remember the formula, because you can kind of remember that almost, it's as though you could actually cancel them out, even though you can't, but it's a kind of a useful rule to just memorize the formula. But now it's sort of more convenient to use the old notation, because I wanted to emphasize that it looks very similar to the old formulas for partial derivatives, which I wrote here. So in fact, there's no mystery. The rate of change in the general vector is a combination of the rate of change in the x direction and the y direction. And in retrospect, what else would it be? I mean, if you look at this formula, you see that it's very natural. Suppose you already know the rate of change in the x direction and you know the rate of change in the y direction. What will be the rate of change sort of in the middle if you go 45 degrees to x and y? Well, clearly it will be just sort of combination with equal coefficients. Right? Both of them will contribute in the same way. The point is, like, which coefficients should we choose? Well, the coefficients we choose will be coefficients of the unit vector. So the square root of a squared plus b squared is 1. That's how we agree from the beginning to define direction by unit vectors. And so then we use those components as the weighting factors. You can think of this as the weighting factors. Each of the two partial derivatives contributes to the rate of change with respect to the vector ab. And they contribute with the weighting factors a and b. In other words, if a is greater than b, then the first partial derivative will contribute more. And will contribute exactly proportionally to the difference to the ratio between a and b. So that's the formula that we get. This is the formula for the directional derivative. Okay. And now we can, first of all, calculate directional derivatives in practical situations. Okay. And we can also discuss the following question. In which direction u do we achieve the largest or the smallest rate of change? Right. So the key to answering this last question is to understand that this looks like dot product. And it is actually dot product. Right? Because we have already a and b as a vector, the components of a vector, namely the vector u, our unit vector. And then if we put the two partial derivatives together as components of another vector, okay, we can then see that this formula is actually nothing but the dot product between these two vectors. Right? So let me take the two partial derivatives and put them together as components of a vector. A very natural thing to do. You think, why haven't we thought about this before? It's the most natural thing to do, because we know that when we have, to get a vector, say, on a plane, we need two components. And here there are two natural components because there are two partial derivatives, x and y. So why not put them all together into one single vector? That's this vector. And then we have our vector u. If we take the dot product between them, we'll get precisely this expression, obviously. So this is a dot product between our original direction vector and some other vector. So it looks like this vector is important. Okay? So we have, in fact, we'll introduce notation and terminology for it. This vector is called the gradient vector. Gradient vector. For the function f at the point x0, y0. And we will introduce notation for it. Nabla f. And to emphasize that it's a vector, we put an arrow like this. Okay, so this is the gradient vector. So what have we learned so far? We have learned that, first of all, in addition to two partial derivatives for functions and two variables that we have studied before, there are also derivatives with respect to a given direction vector, which we choose to be a unit vector u with components a and b. This derivative is nothing but the rate of change in the direction u. It's given by this formula. It can also be thought of as a derivative of the function f with respect to some auxiliary variable h if we write x and y as functions of h in this way. And finally, we have a formula for this directional derivative as a dot product between our original vector ab, the direction vector ab, and another vector which is determined by the function f and the points x0, y0. This vector is just has two components which are nothing but the partial derivatives. This vector is called the gradient vector. Okay. So what is the geometric significance? So you ask, what does this formula mean? What is the geometric significance of this vector? And how can we use this formula to answer various questions about the rate of change of our function? Okay, and here I have to explain a very important interpretation, geometric interpretation of this gradient vector. And the interpretation is that this vector, this is a normal vector. This is in fact a normal vector to the level curve of f at the point x0, y0. Okay, so let me explain this. Yeah, bless you, exactly. I'm just thinking if this blackboard is big enough for me, maybe I should. Let me save it for something else. Let me go. Let me use a bigger one. So first of all, let's talk about level curves. We have a function in two variables, which has a graph. Okay. So for instance, so let's say it's an elliptic paraboloid or something like this. Now, when I want to draw it, to give the illusion of it being 3D instead of 2D, what I usually do is I draw the circles, right? To give the illusion of three-dimensionality. What are the circles? These are the level curves. These are the curves which we get by intersecting this graph by a plane parallel to the xy plane. So for instance, this is intersection of the graph with a plane z equals some, let's call it z0. So let's say our point could be somewhere here. That's our point x0 and y0. And this is the value of the function at this point. So we'll call it z0. So z0 is actually f of x0, y0. But now we look at all points on the same graph which share this value of z. What does it mean? It means that we just cut it by a horizontal plane, which is at the level z0. That's why we call it the level curve, because this is a level, it corresponds to a fixed level of the function. Okay. So in other words, this is a curve which is given by the equation. The equation for this curve is f of xy is equal to z0. Now, let's be a little bit more precise. The level curve actually lives in space, right? The level curve is in three-dimensional space. It does not belong to the xy plane, usually, unless the level is 0. If the level is 0, then of course it will be part of the xy plane. What I've written here, on the other hand, is a curve on the xy plane, right? So to say that this is the equation for the level curve is not strictly speaking correct. More precisely, this is the equation of the curve which I obtained by dropping this level curve onto the xy plane. In other words, what I can do is I can just drop this, take the projection of this level curve onto the xy plane, so it has exactly the same shape. So in this case, let's say it's a circle, let's say, or maybe an ellipse if you want a more general elliptic paraboloid. And so this is going to be exactly the same circle, of the same radius, or the same ellipse, except that this guy was living at level z0 and I just dropped it to level 0. So now it's on the xy plane. So oftentimes, when we talk about level curves, we will not distinguish between level curves as the curve which lives on the graph and its projection onto the xy plane. Because in some sense, once you cut it by the plane parallel to the xy plane, it sort of lost its three-dimensionality. It's become an object which is better to think of as an object in the two-dimensional ambient space. So to be exactly correct, we would have to say that this curve, living on the graph itself, in the three-dimensional space, is defined by two equations. The first equation is z equals z0. That defines the level. That's this plane by which we cut this graph, right? Plus the equation f of xy equals z0. But oftentimes we'll forget about this and just look at the projection at the corresponding curve on the xy plane. So that's the level curve. And now what I'm claiming, except the way I drew it is not, it's not very good because it would have to go through the point x0, y0. And my picture is very misleading, in fact. Right? So it has to be more like this. The question is, what do you want? Something that looks more beautiful or something that is correct? So I'm afraid we have to do something have to do the correct one instead of the beautiful one. So maybe let me just erase it and didn't do a good job at the beginning. Like this. Something like this. As long as I don't make any sharp corners, I think. Is it okay? Okay? So yeah, so this is very important, of course. This curve has to go through the point x0, y0 because this was the original point on the level curve. That's why we talk about the level curve to begin with, because of this point. We look at all other points which share the same value of the function. Okay. And so now what I'm claiming is that if you draw the gradient vector, nabla, starting at this point, then it will be exactly perpendicular to this level curve, which is to say that it's perpendicular to the tangent line to this point. And that's the geometrical significance of this gradient vector. Okay. So now we're getting in a kind of confusing territory, because now we're going to have an interplay between different objects, between tangent lines, tangent planes, and various normal vectors. So I want to sort of set it all straight for you. So this is the first result that I'm going to emphasize, which is that this gradient vector that we discussed, f sub x and f sub y, is normal to this curve. It's perpendicular, which is what I wrote here. Normal vector to the level curve of x at x0, y0, given by the equation f of xy equals z0. Right? So this is the first fact. Now I want to relate this fact to another fact, which we realized 2 weeks ago, about tangent planes to the graph. And that fact is the following: that the vector f sub x at x0, y0, f sub y at x0, y0, and -1 is a normal vector. To the tangent plane, to the graph of f at the point x0, y0. Okay? And I want to explain that these two things are very closely related to each other. And in fact, one implies the other. So you see, and this is a very important point to understand, that at this, we look at this graph, and we have this point on the graph. Okay? We have this point on this graph. Because the graph itself is two-dimensional, there is a tangent plane to the graph, which I'm not going to try to draw, but it's like this, right? Tangent plane to the graph. So in fact, let me use this as a model. For it. Okay? In other words, I will not have the paraboloid. You'll have to imagine the paraboloid somewhere here, right? But think of this as a tangent plane, which is missing in that picture because it would be too messy to me. So this is a tangent plane. Okay? And the paraboloid goes like this. Remember I brought the vase last time, or whenever, 2 weeks ago. So there's a paraboloid which goes like this. And this plane touches that paraboloid at one point. Let's say at this point. So this is the fact number 1. Fact number 2. The paraboloid